Hello everyone and welcome back to this series of videos on the Solow growth model. Specifically in this video, we are going now to derive the output per worker equation. Until now, we've always dealt with aggregate equations, such as, for example, when we talk about output in aggregate terms, we refer to our usual production function where we use big capital letters to determine the different parts that make up our production functions, such as capital, such as labor, such as output. However, we know that variables in like aggregate terms might not be as useful for making, for example, cross-country comparisons and for comparing economies and to see evolution patterns. So that's why we actually need per worker equations. So that we can account for different countries having different sizes, and we can, for example, we cannot directly compare the economy of China, which has such a high population, let's say, compared to a smaller country such as even a smaller geographical country such as, I don't know, let's say Italy. Italy has something like sixty million inhabitants, while China has more than a billion. Of course, China's GDP is going to be greater than Italy's GDP, but is it actually like a good method of comparison? Using aggregate measures instead of accounting for different, let's say, worker sizes and population sizes, it actually is not. Which is why we are now going to delve into the derivation of this output per worker equation. So we're going to start with our usual friend, our Cobb-Douglas production function. And we are now going to divide both sides of our equation by the total labor that we have available. So we're dividing by LT on both sides so that we are going to obtain on the left-hand side small yt, which is our output per worker, because we know that if we divide the total by the number of people that are working, we are actually going to get some kind of per capita measure. But then here on the right-hand side, we need to do a couple of manipulations. So of course, it's as if we are now multiplying our full production function by L to the power of -1. Because if we take it up, it's as if we're writing it to the power of -1. So we are now going to combine the exponents of L. We're going to sum them up so that we are going to obtain a kt to the power of alpha times lt to the power of 1 minus alpha minus 1. 1 cancels out with the 1 so that we are left with minus alpha. Now look, if I want to remove the negative exponent here, I can rewrite my lt as 1 over lt to the power of alpha. And since both kt here, let's use a different color, both kt and lt have the same exponent, I can use the law of indices and write them within a unique parenthesis. Everything to the power of alpha. Different base, same index, same power. We can write it as a unique fraction. And what we have obtained here, this fraction here, is capital divided by number of workers, which means we've obtained our small kt, which is indeed capital per worker, for a very similar reasoning that we did here for our output. So now to combine everything, combining all of the steps, our final result is yt equals to our total factor productivity, our A, times small kt to the power of alpha. And this is our output per worker equation. so that now our production function doesn't look like doesn't directly show two factor inputs anymore. And for notation purposes, we usually rewrite it as a small f, so function of small kt. So recalling though that this kt is capital per worker. So a common question that a lot of students have is, did labor disappear from the model? Did it actually happen? Well, it did not. It did not disappear from the model. It's just invisible because it just got kind of included, it just got absorbed by this small kt, which by itself is actually big K over LT. So it's not that we write our capital per worker equation, our output per worker equation in this way because we don't want to include labor anymore. We are still including labor, just in a different way. We are kind of taking it for granted, not for granted, but we are kind of absorbing it in this single variable. I hope this was useful, and I will see you in the next video where we're going to actually start thinking how to apply all of these equations that we have derived until now.